Our objective today is to talk about the antiderivative problem. We've talked for many chapters about finding the derivative of a function. Now we're going to consider the inverse problem. Given a function, find a function whose derivative is that function. Okay? Well, first let's define our terms, and then we'll talk about the antiderivatives that we can figure out, and then other ways of finding antiderivatives, and application of antiderivatives to sailing and automobile crashes. Okay, so basic idea for today is the idea of antiderivative. You have a function, as usual, we'll call our function little f. The antiderivative for that function is another function, capital F, such that the derivative of capital F is little. It's a function whose derivative is the given function. form constant times x to the power, okay? And whatever those constants are, the derivative will be a times r times x to the r minus 1. And what we want is for the derivative of capital F to be equal to little f. So what we want is a times r times x to the r minus 1 equals x to the third. And can we choose an a and an r to make this true? Well, if you look at the powers here, we would need r minus 1 to be equal to 3. Okay, well, that So now we know antiderivatives of power functions, and we know antiderivatives of exponential functions. But we want still more, right? We'd like to find antiderivatives of trig functions and inverse trig functions and all kinds of good stuff, right? Well, how about logarithmic functions? You're satisfied? Well, I'm not satisfied. How about logarithmic functions? Well, I told you at the beginning that this function, x times ln x minus x, is an antiderivative. I didn't tell you why, but we were at least able to verify that it is, and once we know that, we can go ahead and carry that through. So can we use that to find an antiderivative of another logarithmic function? This is not obvious, the fact that this is an antiderivative for this, and if you want to know it, where it comes from, you really have to take Calc 1, or Calc 2. And like I said, I'm teaching Calc 2, so you could take it in the fall. But using the fact that any logarithm to any base can be written as a multiple of the natural logarithm, and the fact that we know antiderivatives for the natural logarithm, means that we can find antiderivatives for logs to any base. Right? If I have f of x being log base a of x, I can rewrite that as natural log of x divided by the natural log of a, which is the same thing as 1 over the natural log of a times the natural log of x. And 1 over the natural log of a is just a constant. So I can take that constant and multiply it by an antiderivative for the natural log. And I know what an antiderivative for the natural log is. It's x times ln x minus x. So what I get is that an antiderivative for log base a is x times log base a of x minus 1 over natural log of a times x, again, plus constant. Now, does the constant get divided by the natural log of a? Again, if I take a constant and divide it by a constant, still a constant, and it's no more or less arbitrary. Okay, so formally we can find antiderivatives for logarithms, natural logarithms, and logarithms to any base. How about some trigonometry? Remember from differentiation that the derivative of sine is cosine, and the derivative of cosine is negative sine. Well, that shouldn't be too hard to reverse to get anti-differentiation formulas for sine and cosine. So if I want an antiderivative for sine, I just need to take cosine, but then if it were just cosine, there would be a minus 1. So I preemptively multiply by minus 1. So the function capital F of x, which is minus cosine x plus constant, is the antiderivative of sine x. And sine x plus constant is an antiderivative for cosine x. Okay, the hardest part, I think, is to remember which one of them has the minus sign. But as long as you remember your differentiation formulas, these are just the same thing written backwards. Okay. So how about tangent? So the derivative of sine is cosine. The derivative of cosine is a multiple of sine. But we don't have any one of our trig functions whose derivative is tangent, do we? You rack your brain, you're not going to come up with a function whose derivative is tangent, unless your brain is much, much bigger than mine. However, if I said that the antiderivative was the natural log of the absolute value of secant, you'd say, oh yeah, totally, that makes sense. And if you didn't believe me, then you could always just check it by taking the derivative of the natural log of the absolute value of secant. And what is the derivative of the natural log of the absolute value of the secant of x? Well, the derivative of the natural log of the absolute value of anything is 1 over that thing times the derivative of that thing. So 1 over secant x times the derivative of the secant function of x. Okay, and what's the derivative of secant? Secant tangent. And I'm dividing by secant. So what I get is tangent x. See how that worked? Okay, again, how would we know to do this? Well, we'll actually learn this at the end of chapter 5. So this will be one thing you'll know how to do. Not too bad. Okay? But at this juncture, it looks a little bit like a rabbit out of a hat. But at least we can check it. Okay. So what have we learned so far? Antiderivatives of power functions, antiderivative of exponential functions, antiderivatives of logarithmic functions, antiderivatives of some trig functions. We didn't find an antiderivative for secant, and for that we would need some extra work. Let's look at functions which are not strictly elementary functions, but might be combinations of elementary functions. such as a piecewise defined function. Okay. So here's our function. F of x is x if x is in between 0 and 1. And it is 1 minus x squared if x is greater than 1. Okay. So is this function continuous? Well, we're not talking about continuity today. That's always a question we can answer, though, right? Is it continuous? Charlie says yes. Okay, why? They're both polynomials, so each piece is continuous for sure. How do I know that when I glue these pieces together, what I get is a continuous function? Okay. So it's not continuous. Okay. Can I have a function which is not continuous be an antiderivative of or be a derivative of something else? Can you have a function which is not itself continuous be the derivative? Does the derivative of a function have to be a continuous function? Actually, no, it doesn't. So there might still be a function whose derivative is this discontinuous function. Let's see if we can find it. That antiderivative, because it's differentiable, it would have to be continuous, though. Okay, well, we could take the antiderivative of each piece. F of x was x if x is in between 0 and 1. F of x is 1 minus x squared if x is greater than 1. So on the interval of 0 and 1, it should have as antiderivative 1/2 x squared plus a constant. And on the interval greater than 1, it should have antiderivative x minus 1/3 x cubed plus another constant. Now, my font is too big to get both of these on the same screen, but see if you can compare. Antiderivative of x is 1/2 x squared plus constant. Antiderivative of 1 is x. Antiderivative of x squared is 1/3 x cubed. That's how I get these two pieces. And yes, this time I do need two different constants because there are two pieces to the same function. Changing the constant in one of those pieces is going to move that piece up or down. And changing the constant in the other piece is going to move that piece up or down. Okay? Now, this is supposed to be an antiderivative. So it has to be differentiable, and in particular, it has to be continuous. So I need to adjust my constants so that I get a continuous function. All right. We have this information that we're supposed to find an antiderivative where the value at 0 is equal to 1, and it's got to be continuous if it's going to be differentiable. Okay. So the fact that f of 0 is supposed to be 1, does that tell me anything about these two constants? They should equal each other? Well, not necessarily. If I only know it this form, and I don't know what C1 is equal to, what is f of 0? What do I get if I plug in 0 to this formula? I get C1, right? Because 1/2 0 squared, that's just 0, and I get a C1 left over. All right? So f of 0 is C1, and if we are supposed to have f of 0 being equal to 1, I'd better take C1 equals 1. Okay, so that's one of the two constants already determined by that initial value f of 0. How about the C2? Well, we need to make sure that our function is continuous. So to do that, we need to compute the limit from the left at 1 and the limit from the right at 1. From the left, function takes this definition, 1/2 x squared plus constant, which we now know to be 1. And if you take that as x goes to 1, you plug in 1, you get 1/2 1 squared plus 1. That would be 3/2. I need the limit from the right to be 3/2 as well in order for the function to be continuous. The limit from the right, just by plugging in again x equals 1, I get 1 minus 1/3 plus C2. That's 2/3 plus C2. So I need to choose my C2 so that 3/2, the limit from the left, is equal to 2/3 plus C2. That's the limit from the right. Okay? If I can find the right C2 to make this equation good, then I will have created a continuous function. All right, so 3/2 minus 2/3 is 5/6. Okay, is that right? This is 9/6. This is 4/6. Yeah, so C2 is 5/6. All right, so one of the constants was determined by the initial value of the function, f of 0. And the other constant was determined by the fact that we needed to make this thing continuous. Okay. So there's a problem that we sometimes assign. I'm not sure we're assigning it this year, where you have to follow the path of a rocket, model rocket, as you launch it up. And first it goes up into the air, and then it falls freely, and then it has a parachute, and then it coasts gently to the ground. And you have a velocity function which is piecewise defined, and you have to piece all those pieces together to make it continuous. Sure.
For the second part of the piecewise function, why can't you do the same thing and set x equals 0 and try to figure out when you did it?
So the question is, why can't we do the same thing for the second part that we did for the first part? Why can't we just plug in x equals 0 to get C2? Well, when x is 0, the function is not using this rule. The function is not using this rule when x is 0. It's using this one. All right? If we knew, say we needed to say something about f of 2, okay, that's in this interval. So I could plug in 2, and that would tell me what C2 is. But I don't have that information. All I know is that it's continuous. Because the problem says f of 0 has to be 1. That's only because we were asked to find a particular antiderivative. If we were to have f of 0 equal to 2, then we could do the same problem, be different constants. All right. Other questions? Okay. So anytime you've got a piecewise defined function, you can antidifferentiate each piece, but then you have to glue them together to make a continuous function. What if you don't have a formula for the function, but you just have a graph of the function? So here I've got some graph, right? That's my function, little f of x. And what I would like to find is a graph of an antiderivative of that function. What would the graph of that antiderivative look like? Okay. Well, if you play around with it, you might end up drawing something which looked very much like this, except maybe it went higher in some places and lower in some other places. But we actually know how to find information about a function from its derivative. Here I have the derivative. Let me work backwards to find information about the function. Okay, so let me make a sign chart for my red function here, little f, and treat it like it's the derivative of a function which is not pictured, capital F. Okay, so this is our graphing techniques on a function which is just graphed. So if you look at the function little f on the interval 1 to 2, you see that it's a positive function, right? Is that not positive? Yes, it's above the x-axis. It's also positive on 2 to 3. And on 3 to 4, it's negative. On 4 to 5, it's negative. And on 5 to 6, it is positive. And this is all information about the sign, positive or negative, of little f. Now, what does that tell us about big F? Big F has its derivative, little f. So when little f is positive, big F is going to be increasing. Right, little f is positive, big F is increasing. Negative means decreasing, negative means decreasing, positive means increasing again. And this is confusing because we don't see the graph of capital F yet. But we can use the graph of little f to derive features of the graph of big F. Okay. So we can even find that this point here, x equals 3, is a local maximum for the function capital F. And this point here, x equals 5, is a local minimum for the function capital F. Okay. So monotonicity of capital F we can find by using the graph of little f, looking where it's positive and negative. How about the second derivative of big F? Now, we don't see that graphed either, but it is the derivative of little f. If the derivative of capital F is little f, the derivative of little f is the second derivative of capital F. And so I can graph where this function is increasing and decreasing, and that tells me what the second derivative of f is doing. Okay, so is on the interval 1 to 2, is little f increasing or decreasing? It's increasing, so little f prime is positive because little f is increasing. On 2 to 3, positive or negative? negative. Little f is decreasing, so little f prime, that is big F double prime, is negative. Okay. On 3 to 4, negative. 4 to 5, positive, because the derivative has started to increase, and positive some more. So these features of the second derivative of capital F tell me something about the graph of capital F. It says that it's concave up between 1 and 2, concave down between 2 and 4, concave up between 4 and 6. Got it? Oh, you're furrowing your brow and shaking your head at me. Oh, not related. Okay. Something else. Okay. So based on the monotonicity of the graph of capital F and the concavity of the graph of capital F, we can get a picture of the shape of the graph. Yes. Oh, yes. We have 2 inflection points, right? 1 at 2, 1 at 4. So between 1 and 2, the graph is increasing and concave up, and so it has this shape to it. Between 2 and 3, it's increasing and concave down. So it's a second quadrant, right? Between 3 and 4, it's decreasing and concave down. That would be the first quadrant. Then between 4 and 5, it's decreasing and concave up, quadrant 3. And then between 5 and 6, it's increasing and concave up, so it has that shape to it. Okay. And we know that 2 is an inflection point, 3 is a local max, 4 is an inflection point, 5 is a local min, and so on. Does that make sense? Okay. So the only thing we don't know is what the actual values of the function are at these points. That's not something that we can get just by a picture of the derivative. Okay? So without any more information, this is where we have to stop. We could draw something, but it would be kind of ambiguous. To make it a little bit less ambiguous, let's fix one point. Let's say here's the graph of the function, and we'll draw the graph of the antiderivative with f of 1 equal to 0. Again, we're just picking we're changing the problem to have a value of the function. Okay, so we still have the same information we derived before: the shape, inflection, max, inflection, min, and so on. Okay. We're dropping like flies today. I don't know. Maybe I got to stand by the door. So f of 1 is 0. And I know that after 1, the function increases in a concave up manner. So I know that it's going to do something like this until it reaches the inflection point at x equals 2. After that, it's increasing still, but now concave down. So it reaches its local max. Then it decreases in the concave down fashion until it hits another inflection point. Then it decreases some more in a concave up way until it reaches its other critical point, its local min, and then it increases some more. Okay, so here is a rough graph of a function whose derivative could plausibly be this red function here. Okay, so it's still kind of ambiguous because we don't really know how tall this peak is or how deep this valley is. We don't know, based on the graph, where the blue function crosses the x-axis. That much is still kind of ambiguous. But at least we can say broad strokes about the shape of the graph. Maybe not the actual values other than the one that we started with. This much we can tell from the graph. I mean, it is just a graph. Any questions about this procedure? Are you sure? Oh, okay. So what have we done so far? We've talked about antiderivatives of power functions, various kinds of functions, including piecewise defined functions. We've looked at graphs. And let's look at an important application of antiderivatives to what is called in the business rectilinear motion. Excuse me? No, rectilinear motion just means motion along a straight line. Single variable calculus, one variable. So we can't do like motion in the plane or in space, but we can talk about motion back and forth. And lots of times we have information about, say, the velocity of something moving or the acceleration of something moving. And we want to find out information about, say, the velocity or the position of that particle at any time. Okay, so the equations of motion are the position versus time. And maybe we can get that by anti-differentiating velocity. Okay. And now, is that only of theoretical importance? Well, here's a picture of a map from, I'm not sure when this one came from. It says sailing ship routes. And based on where these are all going, you might be able to place what time. Okay, so we've got all these different routes around the world. And consider the problem of navigating your sailboat in a time before GPS. How did you find out where you were on the globe if you are, like, right here, right? How do you locate yourself on the map? Well, there are a couple of ways to do it. To find your latitude, you looked at the position of the sun at noon, how high up in the sky the sun was when it reached its highest point. That's how you measured your latitude. And the way you measured your longitude was you kept a clock fixed on London time, or maybe, I guess it was Greenwich Mean Time. Kept your clock fixed on that time, and then wherever it was noon where you were, you could calculate the time difference between noon here and noon in home, and then that difference is how far you are away on that longitudinal scale. So that's how you pinpointed yourself, or at least located yourself, in the middle of the ocean, and that seems to work pretty well, unless you cannot see the sun. So if you're out there and it's a foggy day, or there's a huge gale blowing up, and you don't have the time or the ability to make a reading of the sun, then you don't really know where you are on that day. So for that reason, sailors kept a log of lots of other things. Here's an example of such a log. So the script is kind of hard to read, and then they use the old style of abbreviations. But this says Tuesday, the 11th day of September, 1781. Okay. And up here we have a notation of course, which is direction, distance, latitude, and then some measure of bearing. And then this is where they were longitudinal-wise. Now, this first column here, these are hours of the day. You start the day at noon, because that's when the sun is up, you can make a reading. And then recordings are made 2, 4, 6, 8. These are 2 bells, 4 bells, 6 bells, 8 bells, and each bell was 1/2 hour. So this is 1 p.m., 2 p.m., 3 p.m., 4 p.m., 5 p.m., 6 p.m., change the watch and eat dinner, all that other stuff. Okay, this column is a measurement of the speed. How did you measure speed on a boat? You didn't have a radar gun? Well, you take a log, and you tie a rope to it, you toss the log off the back of the boat, and you count how long it takes for the log, or how much of the rope plays out in a certain amount of time. Okay, and the rope has these knots in it. The knots are 1 fathom apart, and the number of knots which passes by, that's the speed. You measure your speed in knots. Okay, so this is 4 knots, 5 knots, 4 knots, 5 knots, 4 knots, and then the one here says this is really more like 4.5 knots. Okay, here's the direction. The direction you can measure with a compass, day or night. Direction you can measure with a compass. And so you have your velocity at many times during the day, also your direction. Okay? And so what they did was they were able to piece back their position based on their velocity and their direction in order to find out where they were on a cloudy day. And this process is known as dead reckoning. I'm not sure why it's called dead reckoning, but it's reckoning for sure. Okay? And then when you get to the next day, you make another record, and the day starts over. Okay. So, you know, this looks archaic, right? But this was state-of-the-art until satellites, which is really only like 50 years ago. And GPS satellites, only in the 80s did that become military technology, and now it's stuff that we can count on all the time. Okay. So that's why antiderivatives are important for motion, because many times we have velocity, but we don't have position. Okay, so let's do this abstractly now. Let's think about constant force and the motion which arises from acting on a particle with that force. Okay. So particle is acted upon by a constant force. Find the position and the velocity and the acceleration. Well, Newton's second law is that force is mass times acceleration. By the way, he didn't write it down that way. He said force is the derivative of momentum. Okay, momentum is mass times velocity. So a constant force induces a constant acceleration. That means the acceleration, yes, you can think about the acceleration as a function of time, but it's really a constant. It's just the force divided by the mass. Given that the acceleration is constant, and that the derivative of velocity is acceleration, I should be able to find an antiderivative of this constant to get back to the velocity, right? So let me do that. The derivative of velocity is acceleration. Therefore, velocity is an antiderivative of acceleration, and that acceleration is a constant. So what's an antiderivative of the constant a? Would be constant a times t. I'm using t here as the variable because I'm thinking about time. Okay, so the velocity function would look like acceleration times time plus constant. Now, what kind of constant is that? It turns out, plugging in t equals 0, you get v of 0 equals constant. So that constant that comes up from the antiderivative is the initial velocity, the velocity of this particle at time 0. Now, time 0 means, whenever you start your experiment, whenever you decide time 0 is, v0 is the velocity then. Okay, so velocity is not just acceleration times time, it's acceleration times time plus constant, where that constant is the initial velocity. Now that we know what velocity is, we can take its antiderivative to find position. What's an antiderivative of constant times time? Well, 1/2 time squared times that constant. 1/2 acceleration time squared plus an antiderivative of velocity, which is velocity times time, plus another constant. So we get 1/2 acceleration times squared plus velocity times time plus constant. And what is the constant in this case? Again, when you plug in t equals 0, you get that the constant is the initial position. All right, so our final equation is that the position at time t is 1/2 at squared plus v naught t plus s naught. It's a nice little equation to have lying around. Questions about how I derive that or anti-derive that? Now that we have it, we can use it to answer questions like this. We actually posed this question on the first day of class. Climb up to the top of the Silver Center, drop a ball, and ask yourself, what is the velocity of that ball when it hits the ground? Okay. Well, how is this a rectilinear motion question? Well, we're giving this ball some initial position, that is the top of the Silver Center. We are dropping it. It will be accelerated downwards. Okay. And we'd like to know the time it takes until it reaches down to position 0. All right, we have to assume a few things. I'm going to assume that the height of the Silver Center is 100 meters. You're welcome to prove me wrong, but it's good enough for our estimates. And the initial velocity, we're just dropping it off. We're not throwing it. So its initial velocity is 0. And the acceleration is the acceleration due to gravity. We all know that it's something like 9.8 something meters per second squared. Again, I'm just estimating, so I'll say 10 meters per second squared. Okay, so because I have this constant acceleration, -10, why negative? Because we're accelerating downward, and I'm measuring distances going upward. I can write my equation of motion as initial position, 100 plus 0 minus 5t squared. Okay, so when is position equal to 0? That would be when 100 minus 5t squared equals 0. Or t is the square root of 20. The square root of 20 is 2 times the square root of 5. So, if we want to find the velocity at that time, we take the velocity equation, which is -10 times t. Right? That's the derivative of this. So the velocity at impact, when t equals 20, square root of 20, is just -10 times 2 times the square root of 5. So it's -20 times the square root of 5 meters per second. Okay? Questions about that one? Not so bad, right? Here's another fun one. The skid marks made by an automobile indicate that its brakes were fully applied for a distance of 160 feet before it came to a stop. All right, so we've got some car crash going on. Suppose that the car in question had a constant deceleration of 20 feet per second squared under the conditions of the skid. How fast was the car traveling when its brakes were first applied? Okay. So we have a car, it's crashed. We can measure the length of the skid, it's 160 feet, and we can assume a certain deceleration of the car, and what we would like to know is the initial velocity, right? Who cares? Who cares? Who would want to know that? What? Policemen, insurance agents, right? If we can find without a doubt what the initial velocity is, then we can determine whether the car was speeding. If you show up at an accident, you've got two cars that have collided, and you know you can show that one of them is speeding, well, then that's the one that's at fault. So now that we believe that there's a purpose for solving the problem, let's go ahead and try to solve it. Read the paragraph and see what these words are actually saying. Constant deceleration of 20 feet per second squared says that the acceleration of the car is negative 20. It's going in this direction, and the braking is accelerating it in the other direction, which is why we use the negative sign. Okay? So we can put 0 wherever we want. We will measure time 0 from the moment the car started to brake. All right? So we know, and we'll measure that once it brakes, that'll be position 0 as well. We know that it's going to stop because we arrived at the scene and it was stopped. So there's some time t1 for which the velocity reached 0. And what we want to know is what the velocity was when it started. We also know that when it started, that it's gone 160 feet in the time that it took to stop. And what we want to know is the initial velocity. Okay, so all that information from the paragraph is now distilled into this regular rectilinear motion problem. Acceleration is negative 20. The initial velocity is unknown. The final velocity is 0. And we know the position it takes to achieve that final velocity. Okay. So how do we put this all into an equation to solve? Let's go back to our regular equation. Position is initial position plus initial velocity times time plus 1/2 times acceleration times time squared. And we know that the initial position is 0 because we said so. And we know that the final position is 160. And we know that the acceleration is negative 20. So we can put that into the equation. We get original velocity times time minus 10t squared because it's 1/2 acceleration times squared. And the derivative of this function is v0 minus 20t. All right. So if we plug in the time that it takes for the car to stop, we know that it has gone 160 feet at that time, and we know that it has reached a velocity of 0 in that time. And that is two equations in the two unknown things, t1 and v0. Okay. Now, we didn't ask how long it takes for the car to stop, but it seems like that's interwoven with the question of the initial velocity. Okay, so we need to solve these two equations for the two unknown things, v0 and t1. Okay. Now, usually, if you have two equations and two unknown things, you have enough information to solve for each of them. You have to either solve one of the equations for one of the unknowns and plug it into the other, or you have to do some combination of the two equations in order to get an equation with only one of the unknown things in them. Well, this one, it's pretty easy to take this second equation, 0 equals v0 minus 20t1, and solve it for t1, because you can just add 20t1 to this side, divide by 20. I get that t1 is v0 divided by 20. Then I can take that equation and plug it into the first. All right, I can take t1 equals v0 divided by 20, run it into here. v0 times, this is t1, minus 10, this is t1 squared, equals 160. This is now an equation with just the unknown thing v0 in it. See how I did that? I took this equation, I isolated t1 so that I could plug it into this equation and only have an equation with v0 in it. And this is now not too hard to solve because I can write it as, let's see, v0 squared divided by 20 minus 10 v0 squared divided by 400. That equals 160. Take that equation, multiply both sides by 40. Then the left-hand side becomes 2 v0 squared. The right, this one becomes, let's see, 40 times 10 is 400, so it cancels with the 400. Okay, so I just have v0 squared, and then 160 times 40 is 6,400. So my equation is v0 squared equals 6,400. What's the square root of 6,400? 80. There you go. v0 is 80. And then what are the units? Well, the position was given in feet, and the acceleration was given in feet per second squared. So we end up with feet per second for our initial velocity. If you want to translate that into miles per hour, you just have to multiply by some constant. Basically, you divide by the number of feet in a mile, and you multiply by the number of seconds in an hour, and you get that this is approximately 55 miles an hour. So if this happened on a highway, we can't say that the driver was speeding when the crash happened. Does that make sense? Okay. Well, let's summarize the antiderivatives that we know so far. We know that anytime you have a power function, its antiderivative is the next higher power function, except in the one special case of 1 over x, its antiderivative is the natural log of the absolute value of x. We know that the antiderivative of any exponential function is another exponential function plus constant. If that exponential has a base other than e, you have to divide by the natural log of that base. We discovered that the antiderivative of natural log of x is x times natural log of x minus x plus constant. And so we can use that to get the natural log base a, the antiderivative of the logarithm base a of any x. Okay, sines and cosines we also did. Tangent we were stumbling upon. And this is about all we know for antiderivatives of elementary functions, yeah? Is this a typo? What's wrong? Oh, r can't equal -1. Yes. Eagle eyes. Very good. I'll fix that. Okay. So antiderivatives, we've demonstrated, is a very useful concept, especially when we're doing motion problems. We also learned how to graph an antiderivative of a function given the graph of the function. These are both nice final problems. The whole procedure of antidifferentiation is somewhat complicated. It's a nonlinear problem. We can't always compute antiderivatives. So if you really want to learn the full story, the state of the art as it is for antidifferentiation, then you have to look at Chapter 6, which would be Calc 2. Okay, so that's all I have.